All right, so good morning, everyone. Thanks for coming. I'm Pedro. I'm a software engineer here at Meta. I've been working in Velox for the last, I guess, almost 5 years. So yeah, super excited to see so many familiar faces here. Even more exciting to see new faces. Thank you guys for coming and taking the time. I'm going to be talking a little bit more about the investments we've been doing in kind of accelerating AI and machine learning workloads. Before that, I think just echoing Ali's and Sridhar's words, just thanks everyone for coming. We really appreciate you guys taking a couple of days out of your busy schedules. That was just amazing to see how fast the community has grown. So yeah, I really appreciate you guys taking the time. So getting back to business, I'm going to be focusing on just describing some of the work we've been doing at Meta and the community and kind of accelerating all types of AI and machine learning workloads from a Velox perspective, but also more broadly as a kind of research community and query processing in general. So Velox has been around for almost 5 years, so we can already talk about Velox in terms of Velox history, which is pretty cool. If I look back and look at kind of the different points in time and different things we did as a community, we can sort of group the things we've been working on in 3 different moments or 3 different phases. First one was just the early days when we were bootstrapping things. There was a lot of work on just getting the right memory layout, working on type systems. There was a lot of work on just expression evaluation, UDF execution. And we started using Velox. And the first system we integrated inside Meta was a stream processing system called Xstream. And that was a lot more about, like I mentioned, expression evaluation, UDFs, and things like that, right? So we had to build the foundations to kind of build more complicated types of processing, right? So the first couple of years from 2020 to 2022 was a lot of work on just that, getting the kind of the foundations, the data representation part really consistent and really strong. There was a lot of work on just aligning Velox's memory layout with Arrow's layout, making sure that they're compatible and things like that. Moving on a couple of years, what we've been working on is just supporting large-scale SQL workloads. There's a lot of work on just supporting relational operators, things like joins, hash joins, merge joins, very efficient table scans, merge sorts, and all sorts of things you need to implement large-scale relational engines. So from 2022 to 2024, there was a lot of work on integrating Velox inside Presto, which is a Prestissimo project we've been talking about. On the Prestissimo side, inside Meta, we got to a point where today we're already running about 70% of all Presto batch workloads already running Prestissimo, right? So it's not a prototype anymore. It's not a test system. It's actually a pretty battle-tested system already. We're planning to migrate all the workloads to Prestissimo by the end of the year. Later on today, we have a talk by Amit, who might be here or maybe not yet, but he's going to tell you all about the Prestissimo journey, how we've been going about replacing all the Java engine by Velox. We've been working pretty closely with the IBM team. Prestissimo is also available on IBM at the watsonx data cloud, so we made a lot of good progress there. Outside of Prestissimo, we've also been working with the Gluten community. I guess last year, Microsoft also announced that Velox running through Gluten is also available on Microsoft's Azure cloud. Google later on announced that Velox can also be used on the Google cloud. So on both Presto side and Spark side, we've been making a lot of progress on not just running benchmarks, running TPCH, TPCDS, and things like that, but actually having something that can be used by production, by real customers, and by real workloads. So we made really good progress. Sort of fast forwarding to today, we're now living in a world where AI and machine learning became the largest customers. So we always say that data's largest customer today is AI and machine learning application. And that means that if you look at most of the large-scale lake houses, most data and most tables nowadays are training tables. Also, most compute or just most of the computation goes into cooking training tables and feeding training tables to training frameworks like PyTorch. So the lakehouse has become an AI and machine learning lakehouse. Not just those are the main or the biggest workloads today, but they're also growing the fastest, right? So if we need to optimize for something, if we need to focus on one customer, one type of workload, that's where we need to focus on. So that's why we're making this entire conference. The idea was making VeloxCon about how do we accelerate AI and machine learning, just because this is data's main customer nowadays. So then we got to sort of a third moment in Velox history, and in a world where we need to accelerate AI and machine learning. The questions are, of course, how can we get Velox and how can we use Velox to better accelerate or to better support this type of workload? But not just that, but also how can we extend Velox and what are the new tricks we need to add to query processing to be able to process those things more efficiently, right? So this is a lot of the work we've been doing in the last, I guess, a year. And that's what I want to focus and summarize on this talk. So basically just leaving this message of if we need to optimize for something, if we need to accelerate something, accelerating AI and machine learning are probably the most impactful thing we can do as a data community just because of where the industry is today. So before I describe some of the work we've been doing, just as a quick background on how sort of the machine learning data workflow works. This is a little more centric in machine learning applications for recommendations and ranking systems. But those things are also, there's also a good degree of similarity with other applications of machine learning like Gen AI and content understanding. But the workflow is a little more about supervised learning for recommendation systems, right? But essentially when you have those, this type of machine learning applications, you have those programs called models. And models make predictions, and we serve those predictions to users. Whenever you make a prediction, you need to specify parameters, which people call features, right? So you pass the user features, we make predictions, we serve those predictions to users. Whenever we make a prediction, we log the fact that we made a prediction along with all the features used in this process. We ingest all this data in the lakehouse. We do some data preparation. We generate new training data, and we feed this training data to train new models, right? And then whenever you train a new model, you validate this model, you make sure that it behaves the way it's supposed to behave. You go ahead, deploy to production, start serving traffic, and then you start capturing more training data, right? So you have the cycle where you have models, you keep capturing this data, training new models, and the more data you have, the more data you can feed to trainers, usually the better the recommendations you can serve to customers. In this process, there are two main workloads that you use in this entire workflow. The first one is whenever this data lands on the warehouse, there's this process of kind of cooking, preparing those training data sets. There's usually a degree of taking experimental features, adding to the training data set, running many iterations, trying different models, throwing them away, trying them again. So there's this part of once the data land in the warehouse, curating and creating the actual training data set. So this is what we usually call training data preparation. Another big workload is what we call training data loading, which is essentially this idea of once you have the training tables on the warehouse, you need to read this data, and you need to feed them very efficiently to trainers. So those are kind of sort of the two main workloads in this data workflow. And those two are highlighted here. Just this part of how do we efficiently transform and prepare training tables, and how do we efficiently feed those training tables into PyTorch or other training frameworks. So the first one is training data loading. Like I mentioned, the idea is just getting the data out of the warehouse and feeding them to GPUs. Because GPUs nowadays are the most precious resource you have, you want to make sure that you're not starving GPUs, right? So the system you have to feed this data needs to be very optimized for latency, right? You don't want to keep the CPUs waiting while you're joining, while you're doing pipeline breaks and things like that. If you look at the type of transformations we do in those systems, they're actually very close to other traditional SQL engines, except that, like I just mentioned, we try to not cause pipeline barriers as much as you can, so you don't keep GPUs waiting. Right? So those are mostly streaming operations. But outside of that, the transformations are very similar. It's all very latency sensitive. It's all order sensitive because depending on the order you feed those things to models, the model you train might end up being different. There's a lot of very interesting challenges here. Masha, who's patiently waiting for the next presentation, is going to talk to you all about training data loading. We're going to focus a little bit more on the second workload, which is training data preparation, which is exactly as it sounds, right? When you land this data in the warehouse, what are the kind of preparation, the curation you need to apply to this data before the final training data is ready? In this type of workloads, there's actually nothing new. Whatever you do is just traditional relational transformations. You do joins, you do merge joins, you do expression evaluation, you transform this data. But there's nothing really anything very different from that. Most of this workload already runs in large-scale SQL processing engines. Inside Meta, we run a lot of that in Spark. Some of them we run in Presto, but just kind of traditional large-scale systems that can process relational operations. However, one of the things we identify throughout the years is that Although those things are very well understood by the query processing community, we see that in a lot of cases, machine learning users, they just cannot use or they don't use the engines we provide for a lot of reasons. So what people end up doing is sort of extending, or we even say abusing the engine in all sorts of ways through UDFs, through transforms, or through all sorts of custom code execution to sort of bypass inefficiencies on those engines. And then we got to a point where a lot of the workload we run inside those engines is not the engine itself processing thing, is running custom code. And you can imagine that this may cause all sorts of problems, like it's hard to know what's happening. Sometimes it's even hard to understand where data is coming from. Its reliability is harder. It's hard to even figure out who maintains those things. So this is not a good place to be, right? So this is, in a way, it just means that the engine we develop is not, it's not very optimized or is not very useful for our biggest customers. So a lot of the things we've been doing throughout the last year is essentially trying to understand why do people have to compile their own binaries and run inside the engine to do things that the engine should do in the first place, like filtering joins and all sorts of things. So there was a lot of work on just kind of trying to identify exactly what they do and how we can provide a better engine for people so that they can use the engine in the way it was intended to be used. So I have a couple of slides here. Okay, we've spent some time identifying what are some of the things we found and what are some of the things we are extending in the engine. A lot of this work is already done. A lot of this work is things we're planning to do in the future, but I'll make it clear where we are in each one of them. First thing we found on those tables is that they have a tendency of being very wide, meaning that you have a lot more columns and column streams than traditional or kind of typical analytic tables you have on Warehouse. One of the reasons for that is that whenever you want to train based on those tables, if all the features, if all the columns you need, they're all denormalized, you can just read that table, you can just scan that table, and you can very efficiently fit this table to the two GPUs. Right? While if data is normalized, you might need to join things, and the training data loading process might become a little more expensive and more complicated. Although normalization is, of course, a discussion for some of the workloads, by and large, most of the data sets are heavily denormalized. So not just denormalized, but they usually have a whole lot of columns. So you can imagine that all the features you need to use in the training process, they need to be part of the table. And the more features, the more kind of different characteristics, the more data and more context you can feed your trainers, the best. And in a lot of cases, people don't know what are the features that are most impactful. So it's very common that people just keep adding more and more features to those tables to a point where it's very common to find tables with tens of thousands to hundreds of thousands of different features on those tables. Right? So it's a lot wider than they used to be. If you look at traditional analytic tables, you might have dozens of columns, maybe hundreds of columns in the worst case, but you never had hundreds of thousands of columns. Right? So this kind of breaks the engines that process the data in all sorts of ways. The other part is that the features we use on those training data sets, they're usually very dynamic. So it's very common that people add new features, they remove. So adding columns, removing columns, executing DDL statements and all sorts of, and a bunch of tables that might make part of the entire training pipeline, it's not practical. So what people end up doing is that they model those features as maps. Right? So I have an example here, but it's very common that you have your table, you have some attributes, and the features themselves, they're modeled as a map, and the map is essentially maps some sort of feature ID to the value of your features. Even worse, in many cases, the feature values, they're not just primitive values like integers or floats. In many cases, they are lists or they're maps or they're sequences of other values. It's very common that features might be things that a user has done in the past, like what are the list of the last hundreds of or thousands of things the user clicked on the past. So the values of those features can be sequences. And we have found that the longer those sequences, actually, the more context you feed to the trainer, the better the model quality. Right? So those things are already large, and they have a tendency of getting even larger. And this got to a point where in a lot of training tables, some of the rows, they might be larger than a megabyte. So you can see that the shape of training tables is very different than what they used to be, right? So that's one of the things that kind of breaks the engine in all sorts of ways. What I mean breaks is not that it doesn't work, it just works in a very, very inefficient way. Now the question is, what can we do about it? What are the things we can do or extend to the data stack to better support this workload? So when you're processing data, you can imagine that this is sort of what happens, right? Usually, when you have data pipelines, you have an input table, you read this input table, you map this to some in-memory representation, you apply some processing to this data, you write it back to the other side to an output table. Of course, in some cases, you might have multiple stages, but this is a simple case where you have sort of a map-only query, right? So you have a table, an input table on the left side, you write that back to a table on the right side. So the first thing we did was to evolve the storage layout. One of the things we did was adding this new encoding called flat maps, where the idea is that usually when you store maps in columnar files, you take all the keys and all the values for one particular row and you store them contiguously on disk. And the idea there is if you want to materialize the entire map from one row, you can do that very efficiently. The problem there is that in many cases, for those tables, you store thousands to tens of thousands of features. And when you're training, you usually don't want to read the entire map. You usually train based on a subset of those features. Right? So if you need to read a few features from this map, there's no efficient way to do that with a regular map. So we created this new abstraction, this new encoding type for maps called flat maps a few years ago. This, in a way, is a way to store those maps in a more sort of vertical manner, such that here there's an example. If you just need to read the feature 1, you can just go ahead and just read the sort of the pink region of your file, right? So if you want to, we call the thing feature projections. If you want to project a few specific features, which means you just want to read some keys from your map, you can do those things a lot more efficiently. Right? So this is something we created a few years ago. This is something we use very broadly. The trade-off there is that usually trading some storage efficiency for reader efficiency. Right? So on the read path, you can be a lot more efficient. But on the other hand, the streams you store, they're a little smaller, so they might not compress as well. Second thing we did is we added support for what we call cascading encodings. So the idea here is that you can have, whenever you have a stream of data on disk, the streams are able to describe themselves. So you can have one stream inside another stream inside another stream, and you can sort of recursively or hierarchically apply different encodings to the data. And this is important for those tables because in many cases, because this data is denormalized, you have repetitions between the features across different rows. So if you have support cascading encodings, you can have streams that represent maps or represent arrays, and you can actually deduplicate them by putting them inside an RLE or a dictionary stream, right? So cascading encodings make storage efficiency for those tables a lot better. So we wrapped all those things. We ended up creating this new file format that we initially called Alpha and that we recently open sourced as Nimble. See a few people here from the DI storage team who actually support us. If you have questions, I'm happy to make the introductions. We also open sourced Nimble, I think, about a year ago. So it's an open source project. It's sort of a replacement for Parquet and ORC. And it's a lot more efficient, especially for training tables that have those characteristics. We use this very broadly already inside Meta for training tables. So this is how we evolved, how we store data, the sort of the storage layout of the data. We also did a lot of things to evolve how we process this data. And this is a lot of more kind of strictly speaking the work in Velox. First thing is, of course, vectorization. Velox from scratch, we implemented all the relational operators using vectorization, which is this idea of as you take larger relational operators, like how much you can break this into very concise and very small loops, and very little loops, so that you can execute those things more efficiently. And then CPUs can execute loops that are very tight a lot more efficiently because you have less pipeline bubbles and things like that. So every single operator in Velox is implemented in a very particular way to make sure that CPUs can efficiently process those things. This is sort of a given nowadays. But the second main thing was implementing what we call compressed execution, which is this idea that often when you're processing data, you can leverage columnar encodings of the data to process data even more efficiently. And you can also generate data that's encoded. So some examples here is if you're filtering a data set, you might not need to copy the data to the output. You can just wrap the data using a dictionary or something that just tells you the records that pass the filter. You can do similar things even with joins. If you need to increase or decrease the cardinality, you can do that by just wrapping the data using dictionaries. And of course, the point here is that the fewer times you need to copy this data, because this data is so wide, the more efficient those things become. Right? So we do that very often for expression evaluation, executing expression over dictionary alphabet. So there's all sorts of different places in Velox where we use this trick of, instead of just kind of copying data sets back and forth, to just play with dictionary encodings. And again, this is a lot more efficient for ML workloads because copying each one of those records in some cases means that you're copying an array with 10,000 elements, right? So those things can really add up. So we implemented all those things. Things became a lot more efficient. Like I mentioned, we've been pushing this to Prestissimo. Although this is sort of what we saw if you profile Prestissimo today. And this is not even just machine learning workloads. This is profiling things across the board on every single workload we have on Presto, right? And this is a breakdown of where CPU goes, broken down by operator. So the interesting thing here is that if you look at where most of the CPU is going, is actually just going into table scan and table write. So if you just copy, or if you just look at how much time we spend into table scans and table writes, this is more than 50% of the CPU time, which is sort of surprising, right? You're just, in a way, reading data, mapping this to some in-memory layout. You would expect that the time actually goes in processing those things, right? But we spend a lot of time in just reading and writing those tables back. If you look only at the machine learning workloads that process training tables, this number goes up to 90, and maybe even 95%, right? So kind of virtually all the time, or at least the vast majority of time, goes into scanning and writing table. Part of that is because as we vectorize operators, some of the other operators became so much more efficient that they're a smaller slice of this pie. But then there was a question of why are those things so expensive? So then we optimize the storage layout on the edges. We optimize how we process data, but then the way of kind of mapping the storage layout into in-memory and then doing this, doing the opposite on the writer side, it actually became the main bottleneck. So one of the things we've started observing is that this impedance mismatch between storage layout and in-memory layout has become a bigger bottleneck. It's something that's always been there. It's something that is by design. I think the point is just that as we optimize other parts of the stack and as you start kind of passing a lot more data through this pipeline, this became a more evident bottleneck. Right? So there's a lot of discussions on how can we optimize this part. So just kind of describing this problem a little more, usually the point is that when you're storing data on disk, you use a much wider set of encodings, right? Because usually optimizing for storage space. So usually you want to encode this thing using the most efficient way to encode from a storage perspective. So you can use things like bit packing dictionaries, delta, and all sorts of things. While when you map this storage layout into memory, usually the execution engine doesn't understand all those different types of encodings because the encodings you support on the execution engine are usually the ones that can make execution faster, right? So mapping from this kind of wider set of encodings into a much narrower type of encodings that the execution engine can understand, like that actually adds quite a bit of overhead. So other than evolving the execution independently, the storage layout, we also look into ways of kind of evolving the interplay between those two layouts. There's a couple of things we did here. One is what we call encoding preservation, which is this idea that if you're reading data that, for example, is dictionary encoded, you might just preserve this data as dictionary encoded and deliver this to Velox because Velox can understand those things. Also the opposite on the writer. So let's say that you executed a join. The join actually generated data that's dictionary encoded. In a lot of cases, you might just leverage this encoding as you write this data back. Right? So kind of as much as you can, try to preserve encoders, okay? Try to reuse the encodings between storage and in memory. This is something that makes this problem a little less expressive. Another thing we do very often in Velox is this idea of lazy materialization, which is whenever you read a table, you don't actually read it, you just pretend you read, and you only materialize the data once you actually need the data. And then the idea of doing that is that in many cases, if you delay, right, if you read this lazily, chances are that most of this data will be filtered out, or maybe even all this data will be filtered out, and you don't need to materialize things, right? So of course, if you delay this materialization, you need to decode fewer data, you don't need to decode as much data, and those things become more efficient. Another very interesting thing we observed recently is that, especially when you're processing those machine learning workloads, a lot of data is what we call pass-through. And pass-through is this idea that this is data that doesn't actually participate in query execution. It's just data that we read from one side, we kind of carry through the operator chain, and we write on the other side. So of course, if you're doing things like joins, you need the values of the join keys, but all the other columns you're projecting, you don't necessarily need their values, right? You just need to know what's the cardinality change to those values. So there's a lot of data we saw, and actually most of the data we saw on those pipelines, they're just pass-through data, which is data that you just read, you decode that, you kind of copy that multiple times through the operator chain just to re-encode this later. So of course the question is, this is of course sort of a work that we don't necessarily need. Can we create a different execution model that prevents some of that? So the idea here is that if we had a model that instead of having to carry all this pass-through data through the execution, we could just move them from storage, from one storage layout directly to the output storage layout, things could be a whole lot more efficient. And turns out that you can. This is still a prototype we've been investigating. We call this the wormhole execution model, but the idea is essentially that, right? If you're executing your query, you actually only need the control columns so that you know what is the cardinality changes you need to apply to the pass-through data. But then potentially you can have a process that reads data from one storage layout and maps this straight to an output layout. And then all this, or a lot of this overhead we've been discussing about mapping things from a storage layout to an in-memory layout, you can bypass. So we ended up writing this paper. We submitted to one of the database conferences. Hopefully, I'll be able to share this soon if this goes through. In this paper, we have a lot more details of what this process looks like, how we do this mapping, how generalizable is this framework, what type of relation operators you can apply, and what types of operations you can't. Putting it all together, we build most of those techniques. We build them as part of this PySpark Velox project that Konstantinos is going to tell you all about a little later today. We saw that specifically for machine learning workloads running in the system, we saw something like a 75 speed up over vanilla Spark, which is just a crazy number. It's almost 2 orders of magnitude. On top of that, for some machine learning workloads, we don't need to necessarily rewrite the entire table. We're only adding features, or we're only adding columns. So we also had some work on integrating those things with table layouts so that you don't need to move as much data. Inside Meta, we don't use Iceberg, Delta, Hoodie, or any of the open source table formats, but we have our own file table format called Meta Lake. And Darren's going to give a talk about a little later today about this, focusing on how a table format can allow you to be more efficient while processing machine learning workloads, specifically on when you're injecting features, which is something that people do very often. On top of that, the prototype we put together gives you another 2 to 3x speed up. Like even after you accelerate all those things, then the encoding and decoding CPU overhead becomes even more prominent. So the idea here is that if you put all those things together, you get more than 3 orders of magnitude over vanilla Spark, which is sort of something that is used very widely in the industry, right? So there's a lot of opportunities here if you really look at what the machine learning pipelines are doing and dissect and try to come up with something more efficient. There is a lot of opportunity there. So just wrapping up, we're seeing that with all those query processing techniques, Velox is disrupting how we can, or how efficiently we can prepare those large-scale training data sets. We're seeing like literally orders of magnitude speed up over sort of off-the-shelf engines that are available today in the industry. One thing we learned is that only optimizing the storage layout or only optimizing execution individually just takes you so far, right? So you really need to look at this thing end to end and look at the interplay between storage and in-memory layout, which is something that hasn't got as much attention as it should have got. And lastly, like I mentioned before, I think as a data management community, as AI and machine learning become the largest customer, this is where we need to focus our attention. We're doing a lot of work internally based on the use case we have internally, but we want to collaborate. So, if anyone is interested, if people want to discuss how we're processing any of that, I think this is a challenge we need to tackle as a community. There's a lot of work to be done. Of course, we make some progress, but there's a lot of new things that are coming down through the pipe. As we like to say at Meta, this journey is just 1% done, so there's still a lot of work in front of us, and that's everything I had. Thank you.